Hi guys, this is a video brought to you by Zoe, Eddie, and Jordan from Block 6 AP Physics. So we're going to be doing 8.1 and 8.2, so we're just going to dive right in.
So just to start off, some of the basic differences between conservative forces and non-conservative ones. A conservative force is one that saves energy when work is done. So for example, when you lift up a box, it does negative work on it, mgh. But when you let go and it drops down, it does the same amount of work in the positive direction. Hence, it was conserving its energy when you first lifted it up. A non-conservative force is one that doesn't save its energy. So an example would be friction. Say you're sliding a box across the floor, but once you stop pushing, friction doesn't make it go further back or doesn't push it further back. It just stops there. So the energy it was using back then when you were pushing it in the negative direction, it just stops as soon as you stop pushing. Now another way we can characterize conservative force is that in a closed path, meaning that the start and finish are the same point, no work is done. So an example would be with gravity. If you're lifting a box around in a loop, the whole round trip in the end, gravity will do no work. As long as point A and point B are the same, and non-conservative forces just such as friction are neglected, work and total speed don't change at the end of this trip. Now let's try this quick example that will show to you how non-conservative and conservative forces differ. So to start off, let's start with this first path and calculate for gravity. So we're just going to do this first part, and we'll take the coefficient of friction, multiply it by the mass, which is 70 kilograms, times gravity, 9.81, and then the distance. And that'll give you the work for that one section. And we're gonna have to do that for each part in order to calculate the total work done by gravity on this certain path. Now to skip through the whole entire thing, I'll just add in right here what it adds up to be. And it's going to be a number of negative 2060.1 joules. So now that we've done the first path, let's go ahead and do the second one. It's going to be the same process that we're going to do every piece of the path, horizontal and vertical. And once you calculate all the pieces, you'll get the same exact number of negative 2060.1. So that's the thing about conservative forces. If the start and the end points are the same, with gravity, the work done in total is going to be the same. So now let's do friction, which is going to be a little bit different. It's going to be the same process, but just make sure you count for friction always working in the negative direction. So it's negative coefficient of friction times the mass times gravity times the distance, which is going to give us the work done in that certain portion. And again, we're going to want to do that for the entire thing and add them all up together to get the total work done by friction on this certain path. And what we get is negative 3,304.83 joules. Now one last time, on the second path, for friction again, it's the same protocol. And when we add it all up together, we get a different number this time. As opposed with gravity, we get negative 2,884.14 joules. So as opposed to a conservative force such as gravity, a non-conservative force is going to have a different value for two different round trips, basically.
Now Zoe and I are going to teach you a little bit about potential energy and the work done by conservative forces. So potential energy is pretty easy. Potential energy is represented by the capital letter U, and the general definition for potential energy is stored energy. In equation form, as you see below, the work done by conservative forces equals Ui minus Uf, which is the negative change in U. So the work done by a conservative force is equal to the negative of the change in potential energy. Another neat fact is that you can choose where U equals 0, so make sure you choose points that are reasonable and don't make you do extra math.
So now we're going to apply potential energy to gravity. So when anything is ever dropped, gravity does all the work. This is represented in the equation WC, which is the work done by the potential force of gravity, equals mass times gravity times height, simplified to W equals mg. Why? This can be substituted into the last equation shown on the previous slide, and where negative change in potential energy is equal to the same as the mass times gravity times the height. You can substitute any variable that you need and switch your equation around to fit the example that you are working on. And because of this, you can set u equal to 0. So now we're about to look at the first example. Take a moment to pause and read the question before moving on. So we have our given, which is the mass of 85 kilograms, the height of the building, and the last 100 meters. So we're going to use the equation, the change in potential energy is equal to the mass times gravity times the height of the final position minus mass times gravity times height of the initial. Y final equals the height of the building, which is 3,690 meters. And Y initial is equal to the height, so 3,690 meters, minus the 100 meters, which is 3,590 meters. So now we can find the change in potential energy by plugging into the equation. So we're going to take the 85 kilograms, multiply it by gravity, which is 9.8, and then multiply it by Y final, which is 3,690 meters. Then we're going to subtract that from the second part of the equation, subbing in Y for 3,509 meters. Then we'll find that the potential energy change is equal to 83,300 joules. Now for the second equation, please pause and take a look at the question. So we have our given, which is the energy, which is 9.45 times 10 to the third, our mass, which is the same in gravity. So we're going to use the equation U equals mgh and derive h from that. We'll plug in U for the energy and then divide that by the mass times gravity. After we compute that, we will find that the calories that he ate gave him enough energy to climb 11.34 meters.
Springs. So springs are pretty easy to work with. The only thing you really need to know is the equation U equals 1/2 kx squared, where U is potential energy of the spring, and K is the spring constant, and X is the distance compressed or stretched on the spring. Since the equilibrium position's potential energy UF is 0, the second equation that you see over there that has WC ends up just being UI equals KX squared, and that's your potential energy of a spring. And you also should remember when you're doing these problems that F equals negative KX. So let's test out a fun little example to work with some springs. And remember that Spooderman's mass is 85 kilograms. So the first thing we want to do is write down our given, which is U equals 9.2 times 10 to the fifth, and K equals 294,400. And so we're going to take our equation, U equals 1/2 kx squared, and plug everything in. So U equals 9.2 times 10 to the fifth, and K equals this large number. Oops, let me just fix this really quick. Okay, and X squared. So now we're going to solve for X, and you should get 2.5. Now in order to solve the second part, we should write down 2.5. And then, so for this second part, to figure out how high he's going to go, as you guys should know, we're going to be using the equation for potential energy, U equals mgh. And since we know his mass, we know the potential energy of the spring, and we know gravity, we can solve for h. So we're going to plug everything that we know in, and we are going to get 9.2 times 10 to the 5th equals 85 times 9.8 times h. And then you multiply everything together, you multiply 8.5 times 9.8, and then divide 9.2 times 10 to the 5th by whatever you got, and that should give you your answer.